We're now moving on to the analysis of variance statistics, which are often referred to as ANOVAs. And an ANOVA is used when you're comparing two or more groups or two or more time points. Remember that the t-test can only handle two comparisons, group 1 and group 2, or time 1 and time 2. We can't do 3 groups or 4 groups or 5 groups, but the ANOVA can, so it allows us to be much more dynamic. So if you had a situation where you had 3 groups and you wanted to compare them, why would you not be able to run just a bunch of t-tests? So if you have 3 groups, that creates 3 comparisons. You want to compare group 1 with group 2, group 2 with group 3, and then group 1 with group 3. And you could just run a t-test on each one of those comparisons. The problem is that's really not a very good idea because of the type 1 error. Remember that there's a 5% chance that you're making a type 1 error with every statistic that you run. So if I was to compare those 3 groups with those 3 tests, it basically takes my 5% and times it by 3. So there would actually be a 15% chance that I'd be making a type 1 error with 3 separate t-tests. And in social science, we're not okay with that. Remember that we want there only to be a 5% chance or less a likelihood that we're making that type 1 error. So the ANOVA allows us to compare all of the groups that we have in one test and keeps the type 1 error to just the 5% or less. So here are a few examples of when you would use the ANOVAs. Does room temperature affect test score? Let's say you have one room that has 70-degree temperature, one room that has 80-degree temperature, and one room that has 90-degree temperature. Because we have 3 groups, we would need the ANOVA. Which level of college student skips class the most? Here you might compare freshmen with sophomores, with juniors, with seniors. That's 4 groups. We can't use a t-test there because that would cause us to have a very inflated type 1 error. But you can use the ANOVA when you just have 2 groups. So do men or women spend more time at work? Here you're just comparing men and women and you have the 2 groups. So you could run the t-test or you could run the ANOVA. The ANOVA gives us an F statistic. So remember the t-tests all gave us a t-value. With the ANOVAs we're going to be getting F values. And remember also that the t-tests were meant to compare the means between groups. With the ANOVA we're actually looking at ratios of variances, and we're actually going to compare the variance between the groups to the variance within the groups. So it's getting to the same place but using a slightly different metric. And like the t distribution and the z distribution, there is an ANOVA distribution called the F distribution. So here it is. This is not a normal distribution. This is actually a skewed distribution where the mean is always 1 and a majority of the data falls towards the bottom. And the reason for that is because when you think about the ratio on the last page, the ratio of between groups variance to within groups variance, if the variance between groups and the variance within groups are the same, you would be dividing the top number by the same bottom number, and that would always give you 1. And that's why the mean is always going to be 1 of this distribution. The first specific ANOVA we're going to be learning about is the one-way ANOVA. And the one-way ANOVA will allow us to answer all of the questions we've talked about so far. And so we would come up with a null hypothesis and alternative hypothesis just like before. If we wanted to compare that 70-degree classroom to the 80-degree classroom to the 90-degree classroom on test scores, our null hypothesis might be that different temperature rooms do not have an impact on test scores. And our alternative hypothesis would be that different test room temperatures do have an impact on test scores. We would then use either a formula or the PSPP output to find the F value, and of course in our class we're going to be using the PSPP output. There is some discussion in this week's modules of the summary table that comes with the output of PSPP or SPSS, for that matter, with the ANOVA, because there's a lot of numbers to sift through, and we're still looking for the p-value to make our decision, but you should start to get some sense of what all of those numbers in that table mean from reading the modules. So again, a note about data entry. We're back to 3 groups here, our 70-degree group, our 80-degree group, and our 90-degree group. And based on what we did last time, you might be tempted to do this thing where you stack them next to each other, 1 column for each group, but that's not the way. A one-way ANOVA is much like an independent samples t-test where you have to stack them on top of one another. So I've given each group a number here in this column called temp. So I've assigned 7 to the 70-degree room, 8 to the 80-degree room, and 9 to the 90-degree room. Remember, this is a nominal variable because I've randomly assigned those numbers. And then on the right are the scores for each person who took the test within that specific temperatured room. So we're going to be stacking the data again this week. So after we've run our statistic and looked at our p-value, is it less than 0.05? If so, we reject the null hypothesis. If it's greater than 0.05, we retain the null hypothesis. And usually this is when we report our results, but with the ANOVAs there's actually an additional step. And that step is that if there is a significant F, we have to figure out where are the differences. So if I'm comparing 70 degrees and 80 degrees and 90 degrees rooms, and I get a significant F value, that F value only tells me that there is differences somewhere between those three groups, but not specifically where. It's possible each group is different from the others, but it's also possible that a couple of them are the same and that just one group is different. So in order to be able to deal with this question of where the differences lie, we run what are called post hoc tests. So just to reiterate, if p is less than 0.05, then a post hoc test will tell us where the differences are at. You don't do the post hoc test at all if the p is greater than 0.05. So if you had not gotten a significant p-value, if you had retained the null hypothesis after looking at the f value, you would stop there and move on to the next thing. You would write up your result sentence as normal. But if your p is less than 0.05, you have to do this additional step now that we're in the ANOVAs. So there are numerous kinds of post hoc tests. The book talks about a couple. The one that I want us to learn about is called Tukey's HSD, or Tukey's honestly significant difference. And this is the formula for how to get Tukey's HSD, and it's explained more in the objectives from this week. And that process will help us figure out where the differences are. So once we get to the report results step, when you have a significant p-value for an F test, then you're going to not only need to include the normal statement that reports that F and p-value, but also a follow-up statement that actually reports what you found in the post hoc tests. So with the ANOVAs, there's an additional step, an additional piece to the reporting if you get a significant F value.